Good morning. Here we are learning our subject, that is data mining 3160714. And in that we are learning our chapter 3, that is concept description and association rule mining. So let us recall what we have studied in previous lecture. What we have studied? We have studied we can decide the rules based on the confidence, right? If the confidence of a particular rule is greater than or equal to minimum confidence, we can say the rule is accepted, isn't it? And for confidence, what is the formula? If the rule is, say, apple implies beer, we say that support of apple and beer, and below that we are having support of apple, right? So this division will give us the confidence of this rule, right? And we need to check that it should be greater than or equal to minimum confidence, isn't it? So let us see the example and let us count the confidence of the rules. Fine. Let's check it out. Here is the example given wherein we are having 9 transactions. They are having the T100, 200 to 900 IDs and list of items, right? And for that also the IDs are given. So it is nothing like bread, butter, cheese, but here it is given it as I1, I2, I5, right? Instead of 1 to 5, here it is given as I1, I2, I5, right? See, name doesn't matter to us. We just have to count particular items support count, right? And we should check it out with the minimum support for generating the candidate keys and frequent items for association rule mining. And we can say that when we say that this is the frequent item set, from that we can have the rules, and for them, that is the acceptability of those rules, we need to check the confidence, right? Okay, so let us check it out. Let us consider the 3 item set I1, I2, I5 with support of 0.22. Here what we want, actually what we have to do is we have to count the support count, we have to check the candidate keys, and after the frequent item sets, that is C1, C2, L1, L2, all those things we need to calculate as we have seen in the previous lecture. Then after we have to calculate the confidence of the rules from the frequent item set which we derived at last. Fine. Okay. So let us consider from this point that let us consider this I1, I2, I5 is frequent item set. Which item set? 3 item set, because here we are having 3 items in this item set. Okay. So now from this we want to derive the rules, as well as we want to find the confidence of these rules and check it out whether they are acceptable or not. Fine. So let us first count the confidence so we can have the idea. Fine. Let's see. I1 and I2 implies I5. So what we need to do is, if we want to find the confidence, what we need to do is find the support of I1, I2, I5 divided by the support of or support count of I1 and I2, right? The confidence we can find is, first of all, we should have the support of all these 3 items divided by support of these two, that is the whatever is given before this implication sign, isn't it? So let's say I1, I2, I5. Now you know how to count that, right? Still I am showing you once so you can completely have the idea. Fine. So in this table, let us find I1, I2, I5. Here I1, I2, I5 is there. So count of these three items together is 1. I1, I2, I5, no. I1, I2 is there, but I5 is not there. Let us proceed further. Let us proceed further for 6 transaction, no. For 7 transaction, no. So let us see for 8 and 9 transaction, right? For 8 transaction, we do have I1, I2, I5. In 9 also it is not there. So in this data set given to us, I1, I2, I5 is found twice, right? 2 times it is available. So what do we say is, we are giving this confidence is equal to 2 and divided by what should be that? This is confidence we are finding, right? So we need to find the count of I1 and I2. Fine. So I1, I2, okay, here available. So 1. Here not available, here not available, here is there. So 2. Then not available, not available, not available here. Yes, available in the last transaction also it is available. So we can say 4 times I1, I2 is found together in this data set. Fine. Sequence doesn't matter, as you already know. If it is given as I1, I5, I2, it doesn't matter to us. We only need is I1, I2 should be there. Fine. So they are available 4 times. So we can say the confidence of the rule I1 and I2 implies I5 is 2 divided by 4. And that is equal to 50 percentage. Fine. So is this rule acceptable? What is the condition to accept the rule? That is, the confidence of this rule must be greater than or equal to minimum confidence. Do we have the minimum confidence available here? It is not mentioned, but if I tell you that minimum confidence for this problem set is say 50 percentage, so what we can say is this rule is acceptable because the confidence of this rule is greater than or equal to minimum confidence. Fine. So if the minimum confidence for this problem is 50 percentage, we can say this rule is acceptable. Same way we need to find, say, I1 and I5 implies I2. As we know that if we are having say 3 items, what we have to do is we have to break in the rules where we can have all types of combination. That is I1, I2 implies I5, I1, I5 implies I2, right? This way we can have the rules, right? We need to find the confidence of it. So for this I1, I5, I2, so we need to find the count, which count? Support count of I1, I5, I2. All three together. It is same for all, isn't it? So it will be 2 divided by what is the count of which count? Support count of I1 and I5. So that will be 2 divided by 2 and that is 100 percentage. Wow, that rule is always acceptable, isn't it? Because typically the percentage, that is the minimum confidence, can be given till 100%, isn't it? So it is always acceptable, isn't it? See, minimum confidence must be given in the problem statement. If not, you have to assume yourself. Fine? Fine? Okay. So let us proceed further. For all these rules, we can find the confidence and we need to check whether they are greater than or equal to minimum confidence or not. If they are greater than or equal to minimum confidence, we can say the rules are acceptable. Fine. So now let us have the same problem and Let us calculate all the things. Fine, let's do that. A priori complete example. What do we mean to say? That first of all, we need to calculate the candidate keys. Candidate keys, that is candidate set, I mean to say. Candidate set we will find, then after we'll apply the minimum support rule, we'll find the frequent item sets, then after what we will do, we'll derive the rules, we'll check for the confidence of it, whether the confidence of the rule is greater than or equal to minimum confidence or not, and if it is so, we will accept those rules. Fine. So let us see the example. We can have the idea. Fine. So the same problem statement I have taken here. Fine. Now consider a database D, whatever is given here, consisting of 9 transactions. Suppose minimum support count required is 2. For this particular example, if it is given that support count required is 2. See, support count can be given, support can be given either as support count or otherwise support of this percentage, right? If the count is there, you can convert that to percentage if required, and if the percentage is given, you can convert that to support count. Finding the support count will be easier for you, isn't it? Because we can find the count from this database table, isn't it? So, if in case it is given, say for this example, 22 percentage of minimum support is there, we can convert that to support count of 2, right? 2 by 9 is the way we should find the support count, isn't it? Isn't it? 2 by 9, that is a minimum required count. Fine. So if 22 percentage is given, we should get it as 2 count. And if 2 count is given, we can get in percentages 22 percentage. Right? So what should we do? Let minimum confidence required is 70 percentage. Two things are given, two measures are given to us. One is support, one is confidence, right? Which confidence, which support? Minimum support count is 2 and minimum confidence is 70 percentage, right? Is 70 percentage. So now what should we do? Proceed further with our a priori algorithm. Fine. So we need to find the frequent item sets, isn't it? And then we'll see the association rules, and those must be satisfying the minimum support and minimum confidence, isn't it? Let us proceed. Now here, see the way I have written in this presentation for you, the same way you should write in your exam paper. I have written it that way only that you can follow the same thing, right? So see it properly and please follow the same thing to get full marks, right? For such example. Okay, so let us see step 1, generating one item set frequent pattern, right? So first of all, what we used to do is we used to find the candidate set, right? Candidate set, that is C1. See, everywhere it is written, say C1, L1, C2, L2, C3, L3, whatever is there, that is written, and you also have to write it. Do not forget it, okay? It is the meaningful name to that particular table. And from that, we can have the idea that this is the one item set frequent pattern or two item set frequent pattern or whatever it is. Fine. So please do not forget to write C1, L1, C2, L2. Fine. First of all, we always consider candidate set. So all the items we are putting here for item 1, 2, 3, 4 and 5. That is I1, I2, I3, I4 and I5. Fine. Now what we need to do is we need to count the support count. Fine. So what to do? We need to find the occurrence of these item in our transaction database, right? For I1, let us go back. For I1 item, 1, then 2, then 3. I'm moving my mouse. Please check it out. See that properly. This is 3. Then this is 4th time. This is 5th time. And for 9th transaction also it is there. So what do we say is for I1 item is we can say it is available 6 time in the table. Fine. Which table? Our database transaction, right? So I1 is found 6 times. Count the same for I2, for I3, for I4, for I5. So we can say I2 is found 7 times, I3 is 6 times, I4 is 2 times, and I5 is 2 times, right? This is candidate set, isn't it? This is candidate set. What does that mean? That these items can be potentially frequent. These items can be potentially frequent, right? Now what to do? Compare with minimum support. Whatever support we have counted here, this is the support count, isn't it? Now for that, we need to check for the minimum support. We have already said that 2, support count of 2 is the minimum support. We have said that in the problem statement. Fine. So what should we do? That is, we should check for the support count of this. This is 6 greater than minimum support. 7 greater than minimum support. 6 greater than minimum support. 2 greater than, no, not greater than, but equal is there. It is equal to minimum support. This also is equal to minimum support, right? So here C1 and L1 will remain same because all the items in the C1 are greater than or equal to the minimum support. Fine. So in L1 we'll be having all the items I1, I2, I3, I4, I5, and whatever is the support, that's what we are writing here because all of them are having the support which is greater than or equal to minimum support. Fine. So that's what we have checked. All items with support count greater than or equal to 2, right? Which is already there. So C1 is same as L1. But this procedure we have to show. Fine. Now, what we have to do is candidate set C2. For that, what do we say? What should be the candidate set? Say combining the items, joining the items which were there in L1, right? So now from here, what we are having I1, I2, I3, I4, I5. So let us have all the combinations of joining I1, I2, I3, I4, I5. You can say when we join, we can have I1, I2, I3, I4, I5 together in one set. See, just now, what is this? Is one item set. What is the step for next step for our a priori algorithm is when one item set is there, that is frequent. From that, we need to generate two item set, right? So 1, 2, 3, 4, 5 together cannot be there for two item set generation, right? So what we'll do is we'll combine two items. I1, I2, I1, I3, I1, I4, I1, I5, I2, I3, I2, I4, I2, I5, right? I3, I4, I3, I5, and I4, I5, right? I'm moving the mouse. You can understand it. Let me tell it to you once again. I1, I2, I1, I3, I1, I4, I1, I5, I2, I3, I2, I4, I2, I5, I3, I4, I3, I5. I4, I5. These are the items which are there in candidate set 2, right? That is 2 item set, right? So that's what we have listed here. Now what should we do is we should find the support count of all these things. That is, we'll check I1, I2 wherever the together is available in the database transaction. We'll find the count and put it here. Fine. So here we are putting the count. This is 4, 4, 1, 2. Whatever is there, it is available here. Fine. Now what to do is compare with minimum support. So what to do? Compare whether this support count is greater than or equal to 2 or not. Right? So wherever it is less than or equal to 2, we will remove them, right? Here this is 0, so we'll remove. Here this is 1, so we will remove. Fine. And is there any one else? For last one also I4, I5, it is 0, so we'll remove that. Fine. Okay. So here we will be having I1, I2, 4, I1, I3, 4, I1, I5, 2, I2, I3, 4, I2, I4, 2, and I2, I5, 2. This will remain in L2. Here we can say C2 and L2 both are different, right? Because C2 was having the items which are not frequent. So we'll remove them and we'll have the L2. That is 2 items at frequent pattern, right? Let us proceed further. Now we will have generating 3 items at frequent pattern. 3 items set. Now what we have to do is from L2 we will combine to have 3 item sets available, right? So we can say I1, I2, I3 and I1, I2, I5. But for them, we should check for the a priori property. What is that? A priori property says that if the items what we consider in L3, if all of its subsets are there in L2, then only the combination of those items will be considered in C3, right? They can only be there in L3. Are you getting that? In C3, the items can be there only those which were there in L2. That is, those were frequent, then only we can combine to have the C3. That is the candidate set, isn't it? Okay. So now for this set, we will check what minimum support, right? So we know that 2 is the minimum support count, which is crossing for crossing. Is it crossing? No, it is greater than or equal to 2, right? So this is 2. So it is equality condition is satisfied. And so we can say that L3 will be same as C3, isn't it? L3 will be same as C3. Fine. Now, what do we say? C3 is equal to L2 join L2. The way we are having, right? So we can have so many items in it. I mean I1, I2, I3, I1, I2, I5, I1, I3, I5, I2, I3, I4, I2, I3, I5, I2, I4, I5. But, but, as we know that a priori property must be satisfied. That means the items can be there in C3 only if all the subsets of that C3 item set is available in L2, that is the previous level frequent item set, right? Those only we will combine, we will join and proceed further, isn't it? But other items, for them, the subsets are not available in L2. So we will not consider those things, and we have only considered this I1, I2, I3 and I1, I2, I5, isn't it? So now we are having two items, that is two item sets in the L3. So now we should combine that also to generate L4. First of all C4 and then after L4, right? So based on the a priori property that all subsets of a frequent item set must also be frequent, we can determine that four or lesser candidates cannot possibly be frequent. How? Let's see the example. Let us take one, that is I1, I2, I3. The two item subsets of it are I1, I2, I1, I3 and I2, I3. Since all two item subsets of I1, I2, I3 are members of L2, we have considered I1, I2, I3 in C3, right? Same way we can say that I2, I3, I5. In that, what we say is I2, I3, I2, I5 and I3, I5. See all the combination of this particular item set. But I3, I5 was not the member of L2. So we haven't considered that in C3. Isn't it? So what to do is, after checking all this a priori property for all the item sets, we can say we have considered C3 as I1, I2, I3, I1, I2, I5. Right? Now, now what? Let us consider the L4. Now what to do? For that, we can say we should combine the C3. I1, I2, I3 and I5, right? C4 should be I1, I2, I3, I5. But will we consider that? When can we consider that? We can consider that only if all the subsets of it are frequent, right? So let us check it out. For C4, I1, I2, I3, I5. Joining L3 with L3. So we'll be getting this. For this item set, can we say that all the subset item sets are also frequent? Is it that? Let's check it out. What are the subsets? I1, I2, I3, I1, I2, I5, I2, I3, I5. When we say this, I2, I3, I5. Is it frequent? Is it available in L3? I2, I3, I5. I2, I3, I5. Is it available in L3? No, it is not available. So, we will not consider I1, I2, I3, I5 in C4. And so, C4 is equal to 5. Right? It is empty set. We do not have any item set in this particular C4. Isn't it? You can say, ma'am, try for other, but we have only this combination, isn't it? We have only this combination. So when it is not going to be considered, it is not satisfying the a priori property, we can say we are getting C4 candidate set for 4 item set. We can say that is equal to empty set. So So we cannot proceed further. So all the items are being considered for a priori algorithm. Now from whatever frequent item sets are there, from that we can derive the rules and we can check whether it is confidence, it is acceptable or not, that is using the confidence. Fine. Okay, so what do we use to check? Confidence of the rule is greater than or equal to minimum confidence or not. Fine. So what to do? Generating association rules from frequent item set, right? So let us have our L, that is the combination of our L's, that is L1, L2, L3, right? So L1 where we were having all frequent one item set, that is I1, I2, I3, I4, I5. What about 2, that is L2? I1, I2, I1, I3, I1, I5, I2, I3, I2, I4, I2, I5. And what about L3? That is I1, I2, I3 and I1, I2, I5. So all we have put together and that is our final L, isn't it? Now, whatever is the higher, that is the 3 item set. The last one, what is the latest one? That let us consider and consider the what? What? Rule, right? Derive the rules from that. Okay. How to derive the rules? That is all combinations of these 3 items, right? So say I1 and I2 implies I5, I1 implies I2 and I5, right? All those things will be considered, fine? So let us say we are having the rule like I1 and I2 implies I5. So what we need to do for that? Whether the rule is accepted or not. What do we say? We need to find support count of I1, I2, I5 divided by support count of I1 and I2. So that is equal to 2 divided by 4. How to count that? It is known to us, right? And that is equal to 50 percentage. Now 50 percentage. So rule is rejected. Why is it so? Because in our problem statement, it is given that the minimum confidence threshold is 70 percentage and the confidence of this rule is 50 percentage, which is less than 70 percentage. Fine. It is less than the minimum confidence threshold. So this rule is rejected, right? That's what is written here. It is rejected. Fine. Now we'll do the same for R2. Other rule, that is I1 and I5 implies I2. So we need to do the same thing. Find the confidence and check whether it is greater than or equal to minimum confidence or not. Fine. So confidence, that is equal to SC support count of I1, I2, I5 divided by SC support count of I1 and I5. So that is 2 by 2 and that is equal to 100. Wow, 100%, which is greater than minimum confidence threshold of 70 percentage. Fine. So the rule is selected or we can say the rule is accepted. Fine. So we can do the same for other rules. Fine. Check the confidence. Check it out whether it is greater than or equal to the minimum confidence. If it is so, accept it. Right. Same. Some more rules are given here. Right. What we need to do is confidence is equal to support count of all the items in the rule divided by whatever is available, that is the support count before whatever is available before implication, isn't it? For implication sign, whatever things are there before that, for that we are giving the support count. Fine. So after finding the confidence, we need to check whether it is crossing, crossing, no, whether it is greater than or equal to the minimum confidence or not. If it is satisfied, we can say the rule is accepted, or otherwise the rule is rejected. Fine. Now, a new concept of multiple minimum class support. Now, what is this? Till now, in the problem statement, it was given that minimum support is this one and minimum confidence is this one. Fine. This is what we have learned till now. So now what do we want to learn? This is minimum class, but multiple minimum class. What is that? Let us check it out. The multiple minimum support idea can also be applied here. How to apply? Let us check it out. The user can specify different minimum supports to different classes, which effectively assign a different minimum support to rules of each class. What is this? If we are having, say, food category, like say bread, butter like items, we can say for them, we can set the minimum support as 70 percentage because they are frequent items, or you can say they are frequently being sold. Now, if I say that for diamond necklace, can I set 70 percentage as the support? It should have this much. No, it is not possible because what we are doing is whatever is the support count of that particular item divide by total number of transactions. Now total number of transactions where for bread butter and for diamond necklace, can it be seen? Support cannot be seen, right? For diamond necklace, we can say it is frequent when you can say every day one or two diamond necklace are being sold, right? Every day, say one or two are being sold, then we can say it is frequent. But for bread butter, if we say that from whole day, only one bread butter item was sold, can we say it as frequent? See, so what we want to say is based on the item, particular item, we need to set the support, right? Category, we can say category. The category of the bread butter is a everyday being sold items, and diamond, that is rarely being sold item, isn't it? So we need to have the minimum support for both the items, isn't it? That's what is the requirement of this minimum, sorry, multiple minimum class support, right? So one example, the necklace and bread butter that we have talked of. Now let us consider one more example. We have a data set with two classes. Say yes and no. We may want rules of class yes to have minimum support of 5% and rules of class no to have the minimum support of 10%. So we can have that, isn't it? By setting minimum class support to 100%, we tell the algorithm not to generate the rules for those classes, isn't it? I have given you the typical example of bread butter that is frequently being sold, and diamond necklace, they are rarely being sold, right? So we cannot apply the same rule to all types of items. Okay, so this is a very useful trick in applications. So we will give multiple minimum class supports. Fine. Advantages and disadvantages of what? Of a priori algorithm. It uses large item set property, easily parallelized, easy to implement. Great. So disadvantages: assumes transaction database is memory resident. It requires many database scans for counting one item set. Okay, count in the table. First transaction, second transaction, third transaction. See, scan all the transactions. Again, for say I1, I2, that is say two item set generation. For that also again scan the database. For three item set generation, again scan whole database, right? So what do we say is it requires many database scans. So it will take longer time, isn't it? So if any solution for that, that will make our life simple, isn't it? Our priori algorithm is good. It is easy. It can be parallelized, easy to implement, right? All the things are there, but it requires many database scans. That is the disadvantage of it. Okay. So we should have the methods to improve a priori algorithms efficiency. So what are those algorithms? They are listed here. Hash based item set counting. That is a k item set whose corresponding hashing bucket count is below the threshold cannot be frequent. Transaction reduction. A transaction that does not contain any frequent key item set is useless in subsequent scans. The third one is partitioning. Any item set that is potentially frequent in database must be frequent in at least one of the partitions of database. Sampling, that is mining on a subset of given data, lower support threshold plus a method to determine the completeness. That will save our time, isn't it? That will save our number of scans. Dynamic item set counting. It is add new candidate item sets only when all of their subsets are estimated to be frequent, right? So these are the ways to improve the a priori algorithms efficiency. Fine. We'll see them. Further improvement of the a priori method, that is major computational challenges, multiple scans of transaction database, tedious workload of support counting for candidates. What we are saying is, see, further improvement of a priori method, or otherwise we can say limitations of the a priori algorithm, isn't it? So how we can improve, or what are the limitations? That's what we should say, isn't it? So how we can improve that? The general ideas are reduce the passes of transaction database scans. Second is shrink the number of candidates because we are having large number of candidates. You can say, ma'am, we have considered only 2, 3 candidate sets and we have considered. See, it was the example, right? In reality, we cannot have only 9 transactions in the database, isn't it? So large candidates are there. What we do is we should have the way by which we can shrink the number of candidates. Facilitate, support counting of candidates, right? If we can count the support, for candidates using easier method. Easier method, that means easy to implement? No. The time complexity of that support counting should be reduced, right? So these are the general ways, and what we have done is we have seen the ways, also the algorithms by which we can improve the a priori algorithms efficiency. Fine. So first algorithm of all these, right? All these algorithms. Let's see. Partition. The way we want to apply is partition. What do we want to do is we want to improve our priori algorithms efficiency. Fine. Okay. Because it is having the limitation and we want to improve that. So what do we do? Any item set that is potentially frequent in database must be frequent in at least one of the partitions of database. Fine. So what do we do is scan one partition database and find local frequent patterns. Scan two, consolidate global frequent patterns. Fine. What do we do is we divide the the database, that is we partition the database and find local frequent patterns. Then after, what do we do is we consolidate the global frequent patterns, that is we can say db1 db2 dbk. These are the partitions. Actually when we merge, it is the db, right? So what do we do is we combine the global frequent patterns? No, we combine the local frequent patterns to get the global frequent patterns. Fine. So example we'll see in the next class. That's all for today.